Thank you for the kind introduction. It is my honor and pleasure to be here representing the Global Technology Applied Research Center of JPMorgan Chase. The center performs research across a number of research areas. My talk today is going to focus on quantum computing, but I would like to also, of course, point out the big effort we have in quantum communications, which is led by Charles Lim in Singapore. My goal for today is not to give you an exhaustive survey of the work we do, but rather give you a little bit of a flavor for the kind of research that we do at the center. And I'll have a QR code at my last slide where you can find more information about our work. Let me dive straight in. I'm going to start with quantum optimization. At Global Technology Applied Research, we're performing research across the whole spectrum, from NISQ algorithms you can run today to fully fault-tolerant algorithms which assume things like QRAM and so on. So first on the NISQ side, and this is something I'm going to talk later in the talk, is we're did a recent collaboration with Quantum Solutions Lab at AWS on identifying the potential of Rydberg atom arrays to provide speedups for optimization. Now, on the other end of the spectrum, on the fault-tolerant, let's flip. On the fault-tolerant end of the spectrum, a paper I would not cover today, which was led by Shovnik Chakrabarty, proved the universal quantum speedup for a broad range of algorithms that power integer programming in industry, which underlie commercial solvers like Cplex and Gurobi. And here you have a quadratic speedup in the number of nodes in the search tree that your solver visits. But I'm going to begin with the quantum approximate optimization algorithm, or QAOA, which Scott has called out in his talk earlier as a promising quantum heuristic for optimization. And in this series of work, our goal was to understand the potential of QAOA to offer algorithmic speedups. I'm happy to say that we believe we have demonstrated the first robust evidence that QAOA provides an algorithmic speedup over state-of-the-art solvers on at least some problem. Our results were enabled by a simulator which we have developed in collaboration with Argonne National Lab, and which we believe to be the fastest QAOA simulator out there today. Finally, in an effort to take a step towards realizing this speedup on hardware, we have performed what we, again, believe to be the largest demonstration of QAOA on hardware, at least at the time when the paper came out. So what is this problem on which we were hoping to demonstrate a speedup for QAOA? The particular problem we considered is called low autocorrelation binary sequences. I'm going to define it in a second, but let me give you a flavor for why we choose this problem. It was introduced in the 50s for essentially design of optimal radar pulses. And it's extremely difficult in the sense that the complexity of solving this problem grows very quickly with problem size. Moreover, in classical solvers, and there's a lot of papers out there trying to solve this problem better. If you open those papers, you will see that the runtime of classical solvers is reported explicitly in terms of the scaling of their time to solution, which gives us a clear baseline to compare against. So for example, for best exact solvers, which are branch and bound for this problem, the scaling is something like 1.73 to the n. And for heuristics, it's 1.34 to the n. The nice thing about this is also that we can then take this asymptotic scaling that's reported in the literature and compare this asymptotic scaling to what we see at the small scale in which we benchmark QAOA. And we see that at least the classical solvers already saturate their limiting behavior at this small size in terms of the scaling, which gives us some indication that the scaling that we observe for QAOA will also persist at scale. Now, to give you a context for how quickly the complexity of this problem grows, for maximum independent set, which is the native problem for Rydberg atom arrays, the scaling is, even on general class of graphs, 1.02 to the n. So compare that to 1.34 to the n. It's a big difference. Low autocorrelation binary sequence problem maps very naturally onto quantum computers because it's an unconstrained problem defined on spins. So your goal, given the autocorrelation defined as this quadratic polynomial on spins, the energy is the squared of that, of some of those autocorrelations. And your goal is simply to present a sequence of spins of a given length, so a sequence of plus and minus ones of a fixed length, that minimizes this quartic objective. And so it maps very naturally onto QAOA with no extra overhead. Now, a consequence of the rapid growth of complexity of this problem is that state-of-the-art classical solvers begin to fail at moderate size. So here I'm plotting the best known solution for this problem as a function of number of spins n. And f here is it's a normalized quantity called merit factor. The dashed line is conjectured asymptotic limit. And you see that as you start to increase n, the black dots are the best known exact solutions. So where we know that the gap is 0, this is truly optimal. And the gray dots are heuristics. You can see that at about 200 spins, this line actually starts going down. And we really have no reason to think that this should ever go down. So this to us is a clear signature that this problem becomes classically intractable already at about 200 variables, which means you only need a few hundred qubits to tackle classically intractable instances. Now, to understand the scaling of QA in this problem, we have performed exact simulations with up to 40 qubits. And remember, already at this scale, we have verified that classical solvers achieve their limiting scaling. We use up to 1,000 GPUs on Polaris supercomputer accessed in a partnership with Argonne National Lab. And we observe that the time to solution of QAOA scales better than the state-of-the-art exact solvers, which are branch and bound. Now then, if you combine the constant depth QAOA with quantum minimum finding, you show that you achieve a scaling that's better than state-of-the-art heuristics for this problem. We believe this is the first evidence, that is a robust evidence, that QAOA provides an algorithmic speedup over state-of-the-art classical solvers for some optimization problem. Now, to take a step towards implementing this on hardware, we have run some small-scale experiments on Quantinuum Trap-10 processor. Now, when I say small scale, it's bigger scale than was possible even recently, because implementing the phase operator for this problem requires a lot of gates. Remember, our objective is quartic, and it's high density. So even at n equals 18, so only 18 variables, you're already looking at about 1,000 2-qubit gates. To overcome the issue of noise, we have developed an algorithm-specific error detection scheme, where we're essentially using the natural symmetries of the problem to detect errors that push you outside of this symmetry-restricted subspace. And we see that it significantly reduces the impact of noise on our results. Now let me say a few words about the simulator that we use to perform this work. And really, the central idea is very simple. In QAOA, the phase operator is diagonal, and that's where most of your gates are. So if you can just pre-compute the diagonal and cache it, you can apply the phase operator in one step by just element-wise product. This simple trick leads to better performance than any QAOA simulators out there, both tensor network and state vector. Moreover, the cost of the initial step of precomputation is negligible, because the precomputation is embarrassingly parallel. You're just evaluating your objective on exponentially many inputs, so it's very easy to map it on GPU. So even doing it if you're doing only one evaluation of QAOA is already beneficial. This simulator, which was developed in collaboration with Argonne National Lab, is now open source. It provides what we like to think is easy-to-use API, and we highly encourage you to check it out. Finally, for the last QA result, let me talk about some of the large-scale experiments that we run on Quantinuum processors. Our starting point here was this benchmark, which was set up by DARPA, where the goal was to implement a hybrid quantum classical solver with a large volume. Well, the volume is defined as the product of number of qubits by the number of algorithmic steps that your optimizer performs. So in this diagram, we have two algorithmic steps. So this is 2 times 4, 8. DARPA's goal for the first stage of the program was n times p equals 100. We were able to run n times p equals 320 on Quantinuum H2 device with 32 qubits. Now let me dwell on this number a little bit. So here, we're running QAOA on 32 qubits, and we're increasing number of layers. So as we increase the number of QAOA layers, we get better and better performance. And the performance continues to improve up to about 480 gates which is p equals 10. And then if you go beyond that, sure, the noise overcomes you, and doing extra steps is no longer beneficial. But up to 500 gates, you see continuous improvement in performance. To us, this is a great indication of the progress of quantum hardware. Let me switch gears and talk about our work on quantum annealing. And here, our starting point was this claim, this demonstration of experiment with up to 289 qubits on a 2D Rydberg atom array, which has showed a potential for quantum speed up over simulated annealing. And our goal was really to understand this potential. The problem studied is outlined here. So you have some graph, which is a specific structure that's native to this array. And your goal is to solve maximum independent problem on this graph. So you would like to choose some vertices such that no two chosen vertices are connected by an edge. We have performed extensive numerical studies of this native problem of the annealing device. And we have found, first, that this native problem can be solved to optimality for up to 1,000 of nodes within minutes. So even if you're order of magnitude above where these systems are today, it's still not a difficult problem for classical solvers. You can still solve it with essentially running simplex on a laptop in a few minutes. Moreover, if you take the simulated annealing optimization algorithm that was discussed in the science paper, and you allow it to take advantage of the structure of the graph, remember, is naturally in a two-dimensional lattice, then with this optimization, you completely remove the quantum speedup. And finally, we propose some protocols to systematically increase the problem hardness to make the problem more difficult for classical solvers. Finally, let me talk about some of our machine learning work. And here, we're tackling the problem of hedging, which is an essential tool for risk management in derivatives trading. Now, it's a computationally very challenging problem. And one of the classical state-of-the-art methods for this problem actually was developed at other part of JPMorgan Chase, which is the seminal deep hedging paper, which has received a lot of attention both in industry and academia. Now, in this work, in collaboration with the gracious host of this conference, the QAOA, we have developed a quantum-native reinforcement learning framework for this problem, which has combined efficient encoding for time series data with quantum compound layers, which are polynomially faster to run on quantum computers than they are to run on classical computers in this setting. Moreover, the quantum processor affords natural distribution learning, which performs better than the non-distributional approaches, both classically and quantumly. In our numerical experiments, we observed good hedging outcomes with this framework. And we were able to run some small-scale demonstrations on Quantinuum H1 and H11 and H12 quantum processors. Finally, the developed framework is not really specific to deep hedging and can be applied to a broad range of reinforcement learning problems. Thank you very much for your attention. If you're interested to learn more about our work, I would like to encourage you to check out the QR code where you find links to all of our papers, and as well as the survey which the team has published in Nature Reviews of Physics this summer, which summarizes some of the open questions in applying quantum algorithms for financial use cases. Thank you very much.
All right, thank you very much. So we do have some time for questions. So we already have one. So for the fault-tolerant experiments, how important is large-scale simulation over 50 qubits over a small-scale simulation with just a few qubits?
That's a great question. So going back to that labs paper that I talked about in the beginning of my talk, where we were hoping to demonstrate and were able to demonstrate an algorithmic speedup for QAOA. The tricky part there is that if you only did simulation at small scale, let's say you only did your numerics between 1 and 30 qubits, then you would have seen a scaling that is much better than what we see once we simulate this at scale. So in fact, if you couldn't simulate to 40 qubits, if you couldn't, let's say, use 1,000 GPUs and use large-scale numerical simulation, then you would have actually found the wrong answer. So this is a great example of how you really need to go to large-scale numerical experiments to get an understanding of your algorithm's performance.
Great, thank you. There's one more question that just came in. How does your optimized QAOA simulator scale with system size?
Well, poorly is one answer. It's still exponentially hard, right? The way this works, it's a state vector simulator. So we're just storing the whole quantum state distributed across many GPUs, and then we propagate it. So as long as you can throw twice as many GPUs for each extra qubit, it scales quite well, right? This is why we were able to go to 40 qubits, because this really, the only communication you need is in the mixing operator, and you can use all-to-all MPI MPI calls to make this somewhat optimized. But of course, the inherent exponential complexity of simulation still catches up with you.
Okay, maybe we'll take one more question here since we have time. When do you expect not being able to simulate quantum systems anymore and be forced to use physical QPUs?
I think that's a good question. Scott has touched a little bit on this in his discussion of the sort of the hardest possible thing you can do on QPU, which is these so-called supremacy experiments. And it seems like we're approaching that frontier. So already at 70 qubits, it seems quite plausible that random circuit sampling is hard, even on Sycamore processor with its 2D limited architecture. So we're really approaching the frontier where, for some applications at least, the quantum computer can do something that is otherwise unsimulatable. Now, whether this would be the case for quantum algorithms of interest, let's say QAOA, that's a different question. It's still quite a way off being able to run QAOA that is unsimulatable classically on a quantum processor.
Okay. We have more questions coming in. This is great. So I think this is particularly interesting. What is the working assumption at JPMC about when actual quantum hardware would be used in production?
That's a very difficult question. I think it depends on hardware. We would love to have production-grade hardware today, but it is just not out there. We would like to have a hardware that could run our quantum algorithm for branch and bound and actually demonstrate a speed up. But converting quadratic, it's only a quadratic speed up, into actual production relevant speed up at a cost which makes sense is not easy.
Let's maybe take one or two more. Are you investigating networking of quantum computers with one another?
So we're not a hardware player. We don't build quantum computers. So I don't think that's really a question for us.
OK. And maybe let's just take one last one. Does labs have any implications in the finance space? What are some of these examples?
So our goal for the labs work was really to get a handle on the QAOA scaling as problem side grows. And we really wanted to get a problem for which we can understand the scaling very well. So in this case, labs is a nice problem because we know the scaling for classical solvers. It's very well understood. And because there's only one instance of this problem per size n, the numerics are actually feasible. We don't need to run 1,000 different instances of labs at 40 qubits, each on 1,000 GPUs, to get a signal. We just need to run one. Now, the flip side of this is it's a kind of an exotic problem. And it does not immediately have applications that I can think of in finance. But nonetheless, we're hoping that the speed up that we see for labs is going to be present for other problems as well. It's just much easier to measure the speed up on the labs problem than on, let's say, portfolio optimization.